so my name is Szymaniak, and this is GitLow. If anyone knows what that's referencing, I'll give you another sticker.
Are you talking about like Get Lower to the Metal, like?
Oh yeah, but the song.
Or like the song Get Low, Get Low.
Yeah, you know what date that was?
It's like 2 weeks ago, man.
2002. It was awful.
I'll just take this one.
All right. So I was formerly RITC alumni, and I worked in Rochester for a number of years, and I recently moved out to Chicago. I started working for STC group. My favorite things in life are embedded systems and punk rock, so talk to me later and I'll talk your off. So that's cool. And the whole thing of where this talk came from is that recently I've been faced with multiple situations with situations where I had a microcontroller or SOC bootloader dumps where a cell can compile those symbols and how many strings. And in some cases I didn't even have a memory map of the thing. So if, looking at IDA there, you don't really see any details. But you see a bunch of red things. It's like some addresses that it doesn't really know what's going on with, and that's because those are just memory map peripherals. So I wanted to find some ways that I can improve my ability to comprehend assembly language when I'm reversing. And I'm the type of person that really prefers to dynamically debug things. I have some friends that are just amazing at when they find bug or have a bug, so they just look at code and they can fix it. And they think and they're patient. And I'm just no, I gotta jump in the debugger and just start replicating this. That's how I learn best, and that's how I work best. So I decided to write a unicorn-based debugger, and we'll talk about what unicorn is later. So I can kind of interact with interesting pieces of code. If a bootloader is unpacking or maybe decrypting or just decompressing something into RAM before it executes. I want to be able to just run it and grab it instead of messing around. And there's tons of tools out there, and they're awesome, and a lot of them are for CTFs and things like that. And I tried a couple, but it's really just kind of a matter of I wanted to write something for myself so that I kind of intimately know it and I can tweak it on the fly, and that's why I did that. And there's absolutely awesome tools out there that are probably already doing a lot of this stuff. So what we're going to do here is I want to give you a feel for assembly language programming. I want to, for people who come from a web programming background or maybe don't even have a lot of programming experience, I want to give you a feel of it. I originally wanted to give this talk and have it be 50 minutes of both MIPS and ARM assembly, which is thrown at you, and after kind of thinking about it more, I decided to try and kind of do more of a high-level approach. Then we'll get to the ARM details towards the end as time allows. And all the way I want to kind of exemplify my learn by doing approach. If you're into security or you want to get into security more, sometimes you don't want to focus on how do I hack things, but just how do I learn and just learn to learn. And when you go to these kind of talks and things like that, you don't have to worry about writing down all the commands people are doing. Try to remember oh, okay, I saw this one time and I remember this thing, and now I know how to look it up, and now I know how to learn about it, and focus on that. And then of course I'm going to show some code. And the term assembly language is new to you. I just want to give you some context. So you have hardware, your microcontroller or whatever, and then machine language is the ones and zeros that are executing on that, and the bits in instruction are essentially configuring circuits and logic within some units in the chip to describe the instruction to perform. So we humans, it's kind of annoying to work with. So we have assembly language, which is a little bit easier to read. That's got some mnemonics that describe the instruction, and then the assemblers will give us some cool, convenient things. And then on top of that, we have quote-unquote high-level languages like C, C++. If you ever look up this diagram in a textbook, it's almost like Fortran and stuff too. And then they usually stop there, and then I just added higher-level languages. So we have, if you have interpreted languages, Ruby, Python, stuff like that. So we're going to be right there. So I want to start with just kind of an intro or maybe a review from some of you to computer architecture, and try to do this from a kind of a machine agnostic perspective, so you can just get the sense of how things are going, and then you can apply that knowledge to specific architectures later. So when you're executing on a machine, there's this notion of a fetch, decode, and execute cycle is what you'll hear. So there's a register called a program counter, and it holds the address of what the instruction is you're executing. And that will get loaded into something called a memory address register, so I show that there. And don't worry about right now why that's a difference in one, and we'll actually kind of come back to that way later. But just know that we're going into memory, and we're going to take the instruction out of memory and store it in a register. And a register is it's a one-word location for the CPU. And it's just a whole storage location. It's very fast to access. Unlike going out to memory is costly, and then going out to storage is even costlier in terms of time and stuff. So you go and get that instruction, and then we read it out into an instruction register. So now it's there. So we go to our next phase, the decode cycle. So you're going to take the bits in the instruction, and they're going to go into like different parts of a circuit that'll describe some logic that essentially controls everything else in the machine to perform that operation. And then maybe configure some registers, select them, and things like that. And then we're going to execute the instruction. And there's what's usually referred to as an arithmetic logic unit. So that's got all your arithmetic operations baked into it, and your Boolean logic, things like that. And you see this kind of like memory load kind of in the middle that's kind of weird. What's going on there is you'll see this fetch, decode, execute sometimes with like a middle step where you might have to like load from memory. So if you're like indexing into an array, you'll have to like kind of load that contents from memory in a way. So I kind of just annotate that way. And then write back. There's a stage where you've got to do something with other outputs. You may store back in memory, you'll update your registers, you'll update the program counter, and so you kind of see why the PC is getting updated. So okay, we got this idea of a simple machine. Now, what operations do we need to do something useful? So you need arithmetic operations. Add, subtract, multiply, divide. So we got A times B shift to right 2. Does anyone know what B shift to right 2 implements? Anybody? Divide by 4. Yeah, so free sticker to someone else other than Frank later. I would try throwing them out. We've got some more here. Logical, A is true if B or C is true. Then, if we get more complex things like XOR, we need to be able to access memory. So we need to be able to say, okay, we want to go to the location referenced by variable B, and then we want to index into that array by some value that's in a register. And of course, we need to control flow. So, okay, we know testing some value null or 0, we'll go do this, like our error handling, otherwise we'll go do something else. So, put all these things together, and then that's how we execute stuff. So, to give you some more context, I want to give you like a C-like language, and we're going to go through some line by line. I'm going to describe the operations that are occurring, because one line of code is actually multiple instructions. So, we're going to call this calculate function with some variables, flags, and amount. And the first thing we want to do is we've got to, we're going to pass control this function, so we're going to put the values and parameters of that function in some registers. So here we have registers are 0, 1, 2, and a status register, which has some special meaning. We're going to, what's called a calling convention is kind of describes how, who's responsible for what, who does what when you're, passing control between functions. So we're going to reserve R0 for the return value. So we update registers R1 and R2 with our parameters, and then we're going to move on to our calculate function. But wait, we have AB we need to pass, but we run out of registers. We can't use the status register because that has a special meaning. So this is the idea of the stack. It's a region of memory where if you want to pass information between functions, it's this, you think of the example is always it's like a stack of plates. I'm gonna pass something to you, so I'll stack some plates up, and then you do what you want, and when we're done, I'll take them off. It's kind of the idea. So we'll see that. It's kind of a terrible analogy, actually. So we're going to push AB on the stack. It's called pushing and popping on the stack. So we put the value AB in there. That's our value for C. And then we're going to increment our stack pointer. And that push and pop usually automatically increments and decrements that stack pointer part of this instruction. So then we also need to push the return address when we're done with that function. Where do we want to come back to? So here, you see I pushed the address of if result, the next instruction. So we're going to jump to when the function ends. So we make our function call, and now what do we need to do? Well, A, B, and C, the values of A and B we might need to use later in the code, so it would be nice of us if we didn't mess up those registers when we return. So we're going to push the values of those onto the stack as well, so we can restore them and be nice later to the next caller for the callee. And sometimes you'll just see if there's multiple local variables in a function, you'll push those on the stack as well. However, here let's pretend our imaginary compiler has found this optimization, which we'll see in a second. So we don't actually need to push B. So we're going to test the value of B. Is it greater than 0x80? Let's pretend these are unsigned. So you see the status register changes as a result of an instruction there. So there's a greater than or equal to bit or something that or greater than bit, I guess, in this case. So we're going to say, okay, we'll make a decision based on that, we'll jump, and then let's just clean that out so that we don't, we have a nice clean status register later, so clear that bit out. Next, we're going to implement D equals C minus B. So we'll run an operation to do that. So again, remember that C is actually on the stack, so that instruction is going to be encoded in a way that says, when to describe C, it's going to be the value at what's pointed to by the stack pointer plus 4 in this case. So that's how that gets updated. And now you'll see that, hey, we stored D in where we had B before, so we clobbered it. And yeah, we don't need B anymore, so that's cool. So we do that. Next, we're going to go to the instruction where we want to do this expression. But we can't do like these separate additions all in one. So we're going to first do 1 plus D, 1 increment it. And then, then we'll also negate A, that's a 1's complement. All the 1 bits go 0, all the 0s go 1. So we do that, and then we'll add the 2 and finally put that in R0 and return that value. It's our red. Okay, so now we've got to clean up after ourselves, so we will, we've got to clear the status page too, clean up after ourselves. And then we're going to pop B and A back, so we've restored those registers from the state we were in. We jump back to where we were, and we're going to carry on our merry way. So hopefully now you have a kind of appreciation for what's going to be going on in assembly language before we actually start diving into instructions. So okay, so I want to get into this. What can I use? So Unicorn is super popular. It is a lightweight, multi-platform, so it's supported multiple operating systems, multi-architecture. It emulates, ARM, MIPS, x86, and it's super popular with like CTFs and stuff like that. Although it seems like in the CTF community, people like playing around more with x86 and stuff. So I thought, hey, I'm gonna start focusing on ARM first because that'll be fun. The framework is based on the QEMU codebase. But the two projects are very different intents. Unicorn is a framework that's made for you to kind of, extend things and implement things, whereas the QEMU is kind of, a standalone, emulates things for you. So if you check out the showcase on the Unicorn website, you'll see there's a lot of projects with interest in security and reverse engineering, and there's stuff close to what I've done. And I played around with some of them, and it's kind of one of those things where I like this feature and I like that feature, so I want to kind of just put them all together in one tool. This is awesomely simple and concise API, which is always great when you make an API. And there's tons of bindings. You're going to find bindings for whatever language you love. And I highly recommend that you check out their Black Hat 2015 slides, which are fantastic. Let's check that out later. So I just want to quickly show you some Go code of, let's just take some binary code we found, or we found it in a PCAT file or something. I don't know. So on line 11 there in main, there's some code. We'll just put the binary data in there and get the length of it. And then on line 20, we're going to initialize a new emulator in ARM emulation mode, and then the ARM architecture, and then the mode will set to ARM as well. There's ARM versus thumb mode. We'll get back to that later, but don't worry about it for now. And then on line 26, well, we got to have some imaginary memory to work in, right? So we're going to say, okay, to address 0, let's map 1 megabyte, and that's going to be read, write, execute. You can change the permissions to it, catch exceptions when things are, trying to execute on a real or non-executable memory and stuff like that later. We'll go over that. So we're going to write the code into memory on line 31, and then what's going on in that next chunk of code is I just have a list of register names, the enumeration value that describes that register, and Unicorn's IDs, and then the values I want to put in there. And then for each one of those definitions, I iterate over them, and I write them into the emulator saying, I want you to write R0 with this value, R1 with this value, etc. So you need to get the initial state of the machine. And then finally, you execute it. So there's an options thing there that's a timeout in milliseconds and a count. The count say how many instructions you want to execute. And if you set it to 0, it's just going to keep going until something happens. So in this case, I have the code there. I'm going to assume it maybe goes into an infinite loop where it causes an exception. So I'll say timeout after a second. And then we can print the results. Go read each of the registers. For each register, go printf it. So I print the name and then the value. So, excuse me. So there's the output of running that. So that's pretty cool. We just took some RAM code and in a couple minutes we're running it. That's fantastic. So kudos to the Unicorn people. Capstone is a related project. So this is kind of the same idea, but it does disassembly, and it's made by the same people. So again, simple, concise C API, tons of bindings. It's a disassembly framework, and it's really targeting the people who want to do reverse engineering. So kind of a for us, by us kind of mentality there, and it has all the stuff we need. So again, I'm just going to show you that code we want to disassemble. So it's a very similar process. So you instantiate the disassembler until you're in the ARM architecture and you're in ARM mode rather than thumb. We'll come back to thumb again later. And then this is a very important thing I found. You got to tell it to skip invalid instructions, because if you don't do that and it finds something like that's a garbage instruction, it's just going to stop and you won't see the disassembly of stuff after it, which you're probably interested in. So you can tell it to turn it off and you can customize how it handles that. But that was just one of those things where it took me 15 minutes to figure out what am I doing wrong? It's not going past this something I know is garbage. So then you just call disassemble this code at this address, and you can say like, oh, just disassemble up to 64 instructions. We clearly know that there aren't even 64 bytes there, let alone 64 instructions, but you just set a max and we'll go on its merry way. And then for each instruction in the range of all these disassembled instructions, they'll be sorted by the order. We'll print the address that the instruction was at, so you know where it was. And then the bytes that make up that machine code representation, and then the human readable assembly of the mnemonic and the operands, excuse me. So yeah, there you go. Quick disassembly for you. Super easy. And don't worry about what the code does, we'll get back to that. Alright, so now we can emulate stuff and we can disassemble it. What about writing it? That's kind of about my whole thing. I want to be able to write code and better play with it and mess around with it and understand like, why does this instruction do this? So there's lots of options. There's Keystone, which again is kind of part of that whole community with Unicorn and Capstone, popular in the kind of CTF and reverse engineering scenes, and there's the GNU toolchain. And I actually went with the latter. And the reason for that is I've worked with a lot of the GNU toolchain stuff, and some of the projects I'm interested in, I know they're using it. So I kind of went that route. So hopefully you'll kind of get a different way to go about doing things than you might see elsewhere. So the general process is you write code in a .s file. That's kind of a standard convention, and your editor will syntexify it for you. We'll assemble it using a quick make file, and then execute it using Unicorn. So I just want to show you a quick make file around it. How many people do make or no make? Just perfect. So I'll just kind of quickly go through this. So I like to define variables to make my make files nice and generic and reusable and stuff. So we define the prefix of the command arm-none-eabi. If you're in Ubuntu or something, you can apt-get install arm-none-eabi gcc to get the toolchain, and usually you define cross-compile to say what prefix it is, because if you're doing like a different architecture, it'll be like mips none-eabi. And what that means is ARM architecture, none as opposed to, it's going to be bare metal as opposed to like Linux, and then the ABI, application binary interface, the embedded application binary interface, is kind of just describing some standard ways of storing data structures and things like that. So how they're accessed. So you don't really need to know that, but it's true, I guess. And then next we're going to define what command we're going to run for assembling and how we're going to run it. I actually like using GCC, and then the assembler with CPP option, C preprocessing, so that I can get like pound include, pound define, and all that other good stuff instead of just using raw GNU assembler, gas, notation. We'll then use object copy to extract the binary code. So when we run it through GCC, we're actually going to get an ELF out of it, the format for executable. So we want to just kind of scrape out the raw instructions, and we'll do object copy for that. So we have an alt target. We say, okay, we want to make a file called hello.bin, and if we kind of jump down to line 19, we'll see that okay, to create that, I need to make a hello world.o. That's going to be ELF. But first do that, we got to do line 16, which says we need hello world.s, which we have because it's the source file we wrote, and we're going to run the assembler on it, specify the source, and specify the output. And obviously, you can, if you get people in make, you can do that shorter and much quicker ways, but I want to be explicit. So run those two things, and here's just an example of, you're going to run make, it's going to print the commands out for you, and then, that's the ELF versus the data that we're going to execute. So if we take a look at this in hex dump, you kind of see the instructions and how they're associated with what we see in hex dump. So I just want to kind of show that. So my tool, I don't know if this, it's all right. You're not going to really need to actually see the details, but so this is the tool I've been working on, and it's not quite done yet. I'll talk about what I'm doing forward and when I'm going to release it and things like that. So what I wanted to do is write a Go-based batch execution tool and a debugger GUI. Pro tip, don't decide to learn Go like a month before you talk. No, actually, I think it's a testament to how much I've, coming from a C and stuff like that, it's a testament to how great the language is, because it's been super easy to learn and pick up, and it really wasn't a problem. So you can see the green there, those are kind of the external libraries, like Unicorn, Capstone, and then this cool library called GoCUI, which gives you turnbox support. It gives you little views, and you can update them and just printf into them or printf into them. So on top of that, I built kind of two core components, this kind of little debugger framework that I can then use to expose a batch command execution environment so that I can just script stuff, and then also a GUI with the UI. So first execution way I'm executing there is just specify the architecture, and then I'll auto pick a base address to put stuff at, what code I want to execute. And then as far as like batch execution, I also want to be able to specify the file, but also the initial state of registers, and then this little thing where I say, okay, I want you to map some memory region, I'm going to call it SRAM, I'll give you the address that it's going to be expected to be at, the length of it, the permissions of that, some file name that you want to write into that before we start executing, and then dump it out. So again, like I was talking about, some code getting unpacked or decompressed or decrypted from like a bootloader or something like that, that's kind of what I'm doing there. So I just quickly want to click through it, and can you guys see that array? Is it probably a little tough? So, there's those help commands, and I'm lazy, so all the commands kind of will complete, just based on the first letter or two. You can set breakpoints, you can step, and it'll highlight changes, continue, all the kind of normal stuff. Hey, you screwed up a command, here's how to, run it and stuff like that. So I like well-polished things. I'm trying to work on that, and read and write to memory. So that's kind of the general idea. So all right, now it's time to finally start diving in. That guy's got the idea. That's a bit kind of these. Quick facts, a little bit about ARM. I'm not going to spend a ton of time diving into details. You can go into that. I just want to give you kind of the high level so you can go on your merry way and do excellent work. So it is a reduced instruction set machine. This would be simpler instructions as opposed to CISC. I think x86 is CISC technically, and ARM is technically RISC. There is a user mode and other privileged modes. Not really, you don't have to worry about that too much, but there's no support for unaligned access. So how many people have read the IDA book for anybody? All right, so you probably the whole thing where like if you want to try to trick crappy disassemblers that are going to just do a one pass through, some things you could do is like just put a couple garbage bytes in your code and then jump into the middle of an instruction and go from there. And then if something's just doing one pass to disassemble it, it's not going to succeed. So you can't do that in ARM. So sad. ARM has 32-bit. Well, ARM 32-bit, ARM is 64-bit as well. We're talking 32 only here. That's fixed with 32-bit opcodes. And there's also this thumb mode, and thumb is 16-bit opcodes, and the instructions are more limited, but this yields higher code density. And you think about like the microcontroller space, or if I'm implementing a bootloader, and it's the case that the device is going to go from an internal ROM, it's going to go to a tiny internal SRAM, and then go execute that, so it can bootstrap DDR memory, and then go load code from there. And we want it to be really dense and small code. So the whole idea there is you have denser instructions that they can't necessarily address or jump to larger ranges, but you probably don't need to if you're in that little code. And the reason why that's kind of cool to think about it from the security perspective for us is if you're writing like exploit code, that gives you some more opportunities. So let's say you want to defeat some sort of restrictions on what bytes can be in a payload. Maybe switching between the modes, you'll get be able to get an encoding of something you like better. Or if you're looking for raw gadgets. You can now basically have twice the code to work with. You can, okay, what does this look like if I try to disassemble it as ARM versus thumb? So those are some cool things security related, so I don't want to worry too much. Most instructions take this kind of form where you have the instruction and then some sort of suffix and then the operands. And this is cool. So the suffix can be the condition under which you want to execute that instruction. So if you have like a if something else something, and there's only one operation in those, you can just have the instruction be conditionally executed and not otherwise. So that's pretty cool, right? And that suffix can also denote whether the instruction should update the status register. So remember how I showed fix my thing here already? Okay. If you we want to clear out the status register in that example earlier, right? That's kind of a pain. So you can just have an instruction say that, this one shouldn't update it because I don't want to have to clean it up later. So that's cool. So here's two examples. You have, a branch not equal to label. So we did a comparison, and if two things aren't equal, we'll branch to label. And another example is, adding with updating the status register versus not. So like if you add 2 bytes and they overflow, and are they going to cause a carry bit to BSide, or you could just ignore it and say, no, I was just going to mask it with a byte anyway, so I don't care. So some kind of quick things for you there. So there's registers. You have R0 through R15, and then a current program status register, and an application program status register. There's kind of an interesting relationship between them, where the APSR is a subset of the CPSR, or vice versa. But just know that. So that's just status. It tells you about some things about the current processor states, like whether it's in the CPSR tells you that, like whether it's in thumb or ARM mode, and Giselle mode. Does anyone know what Giselle is? This is fun. Giselle, like at one point they decided, like, oh, we want to be able to run Java bytecode. Like, Yeah, that's not really a thing anymore that they really care about, but I don't know, at the time it seemed like a good idea, so like, if anyone wants to chat later, it'd be fun to like, I've never like, so that's another thing too, where that's a little side here, we have time. So like if you're writing like an exploit payload, that'd be kind of fun to be like, oh, well like we can, you know, if we're looking for, you know, a gadget chain, and we can do it either ARM or thumb, like what about Giselle? So like, that's kind of cool, so I don't know, I haven't looked into it myself, there's tons of material on it, but it'll be fun to look at, right? And there's also, you know, multiple modes, and there's save program status registers, so if like a context change occurs or something like that, you know, there's a variant of that. Just know those exist, we're not going to cover them. So R0 through R12 are general purpose, we can use those in our code as we wish. R13 is the stack pointer, so push and pop instructions are going to work on that, so you know, don't use that for your general stuff unless you want to. R14 is what's called a link register, so when you do, you can do a branch and link. What's going to happen is you're going to do the branch, and then for you, it's going to put the return address in this register. So then if you don't have to put it on the stack manually, unless you're going to do something else that's going to taint that later. So that's cool. And then R15 is our program counter, and you can do a limited set of operations on the program counter, like moving to it or adding to it or something like that, but when you go back, and you're inevitably going to go back to the instruction set reference manual, I assume. There's a bunch of operations that are undefined in R15, so that's kind of cool. Like, what do different implementations do? And studying that might be kind of interesting, right? Okay, so finally some ARM code. It's like, how long have we been talking? We haven't looked at it yet. What are you doing, John? So let's just kind of go this line by line. Now we have a sense of what we're doing. So let's see, add R0, R1, R2. The first operand there is the destination. And then the other ones are like the sources. So we're going to say R0 equals R1 plus R2. So if this registers and execute it, get some addition. Cool. All right, now we're going to rotate R1 by 5 bits. A rotate is essentially, I'm going to have to turn to do this. So you have our register. These are the most significant bits, least significant bits. We're going to rotate right. So we're going to shift right. So these bits actually like fell out of the register. They're no longer in it, and we're going to bring them back around. So that's a rotate. Next, we're going to subtract R3 equals R1 minus R0. And again, you know, this is usually what I think. Yeah, so I think it's 2's complement, sure. And then we'll let exclusive OR, so R2 equals R3 XOR R1. And then we're going to load R0 with the value deadbeef. We'll go back in just a second. And then B dot, so in the GNU assembler, if you use the dot, that refers to the current, it's just saying, that whatever this instruction is, whatever the value PC is. Okay, so this is actually kind of weird. So we're starting with a simple example, and wait, it's already getting weird. So usually you'd use a move instruction, like move R0 to, hex 13, but instead we use LDR, like load data from memory. So if I wanted to, load R0, R1 at an offset of 5, and furthermore, deadbeef, it's 32 bits, and I said that the instructions are 32-bit instructions, so how is that even possible? And so when we looked at that, the output of capstone earlier, you notice that there's another line there, but that's not in the code, and that's on an instruction, that's deadbeef, and it's a little ending byte order because ARM is little ending, and I think though there is technically some modes to do some big ending stuff. So yeah, that's DE, AD, BE, EF. Okay, so our value's down there. What's going on with that? All right. And Capstone told us that although we wrote that thing above, it's telling us that it's saying R0 equals PC, but with a 0 offset. So that doesn't make sense either because that's our current instruction. So what is that about? So usually in this sort of situation, what I've been doing is like, all right, well, I'll go open IDA Pro and we'll see what IDA has to say because guys that wrote IDA are brilliant. Okay, well, it's just showing me basically what I wrote, which is cool, right? Because if you're trying to read someone else's code and you have something that looks more like what they wrote, it's awesome. So that didn't help. And the same thing with Hopper. So Stack Overflow to the rescue, right? I don't know if this is big enough, so I'm going to read just kind of important lines. So the original ARM design has a 3-stage pipeline: fetch, decode, execute. Hey, you know what that is, right? To simplify the design, they chose to have a PC read as the value currently on the instruction fetch address lines, rather than that of currently executing instructions from 2 cycles ago. So this fetch, fetch, decode, execute, you think about it, you can pipeline it, and while you're doing a decode, you can start fetching the next one so that you're a little more efficient. So they have this pipeline going on, so PC is getting updated while you're working on stuff, and It's easier to have the assembler/linker compensate for that 2 instruction offset than to design all the logic to get the correct PC value. So this is basically an artifact of pipelining, and then he goes on to add some cool comments on that. So if you're programming an assembly, and I saw that dot, like, oh, this instruction, you don't have to worry about it, all this is taken care of for you, but if you're reversing something, this is the kind of important fact to know, right? So okay, we're covering our setting now. So now we know that it's not really PC plus 0, it's PC plus 8, and we're actually loading the contents of that memory address into R0. So that's cool, and if you're working with a GNU assembler, I can't really speak to any other ones, but if you do load R0 equals 5, the pound sign there just saying it's an intermediate value, it'll actually give you the move instruction. So you can always just do that and let it take care of picking the right way to do it for you. And so if you look at if you start disassembling code and looking at it, you'll see functions, and at the end of them, just a bunch of garbage instructions, and those are actually data. And usually IDLE will show you like, oh, it's just data, something like that. So that's good to know. So now I kind of want to start getting into some more relevant stuff and writing it ourselves. So let's say you're writing some exploit code, and you want to need to access something back in your payload, but you can't use the absolute address because you don't know where in memory that's going to be. So you need to keep your code position, keep it position independent. And PIE is position independent executable. So I've been writing a MD5 implementation just for fun. So the way I did this was, in the start of all my test codes, because you should unit test everything, right? Move PC into FP is the frame pointer, it's actually R10. So you move PC into a register, it's the very first thing your payload executes. So now we know exactly where we are. But again, you can reference this, where you can actually find the whole thing about PC plus 8 that we just talked about. Okay, now I've got this. So you then assemble all your code, assuming that it's all executing at address 0, and then whenever you're going to go fetch something from your payload or whatever, you just add an FP to it, and just keep one register around for yourself if you can. And then setting up the stack here just so that I can kind of do my little test pictures. So, okay. How do we implement functions? We haven't really talked about that. We kind of saw it a little bit maybe, or might have alluded to it. So there's branch instructions. So there's branch with link, and branch with link and exchange. And I kind of pulled this out of Beyond documentation that link there. You can go into more details. Branch is just an unconditional branch. Just go jump somewhere. Cool. Branch with link is saying, I want you to branch and put the return address in that link register so I have it later. So you can kind of pick which one makes more sense for you. Branch with link and exchange is cool because you can exchange instruction sets. And I think it's, you should double check. I think it's the lowest order bit. If that's set, it'll switch into thumb mode. And if it's not, it'll stay in R mode. And let's see on the next slide here. I'll come back to it in a second. So how do we implement stacks with this load and store multiple? So this is an example subroutine. So store multiple full descending. The full descending is just describing the way the stack works, so don't worry about that. You can get to that some other time. So the way this reads is you have your stack pointer, and an exclamation point is saying, I want you to store these the values on the stack, and then update the stack pointer for me. And I want you to store registers R5, R6, and R7, and the link register. So what's happening is we're preparing to take a function call, and then we're saying, okay, I have the return address from the last function we were in, but I don't want to lose that, so we're going to store that and then some registers that I don't want you to dirty. So this whole idea of calling convention is who's responsible for doing stuff, the caller, the callee, and where they put things. So I'm just going to nail that out again. So then we're going to branch into our function, branch with link, so that the return address is placed in LR, and then when we return back eventually, we're going to load that stuff back from the stack. So we're going to say, load memory and update the stack pointer to move that pointer around. It'll load those contents into R5 and R7, and then put LR into PC. What's cool here is you see that it's not LR, and that's like an argument again, it's PC, because we're taking the old return address and we're writing it into the program counter. So you don't have to load and store the same things you did, so you can use other registers, things like that. So okay, that's cool. So how do we go about using this? So this is some of the code from the MD5 implementation I was writing just to kind of help myself learn things a little bit. And one neat thing to note here is on line 45 there. So that branch with link and exchange, that's not just to switch modes. Branch with link doesn't support branching to an address stored in a register. So if you want to like get the address of a function or a subroutine, you have to use BLX, and you can do that. Again, because things are going to be aligned on like 4-byte words, you're not going to set a situation where that low bit is set or something. So then I just kind of show over here. This is a call function. So it's round up. So you see. I'm storing the things that I'm going to dirty and the link register, do some operations, and then I return. We just talked about line 15. And I highly recommend that you comment your stuff like this. I mean, I know a lot of people are like, if you're in a CTF or something, you're just going crazy, right? Because you don't have time for this. But if you're writing something, like, you're going to lose your mind. So document your input parameters so you can remember what you're doing. And then what's being updated is your output parameters, and then even side effects. Because if you come back to this stuff weeks later, you don't want to have to load up IDA or something to figure out what your own payloads are doing. So let's start wrapping it up a little bit here. Now a little early because I rushed a little bit. We can spend some time going over answering questions, or I'll kind of show the tool a little bit. So what's my roadmap with this Angular tool that I kind of mentioned I'm working on? So I originally wanted to have it ready to go and have people working on it, playing with it, but I think I'd do us all a disservice if I did that. So I'm going to finish up a couple remaining items. I want to get the kind of README nice so you can kind of get the ground running and maybe kind of take some of this content and put that into a wiki. A feature creep right on the plane. I was working on color scheme support for whatever reason, because there's a couple tools that have the opcodes are colored nicely and stuff, and I implemented the whole thing, and there's a couple bugs, so I pulled it out because I don't want to be put the code freeze the night before you talk. Don't touch your code. So probably the second week of May, I'm going to try to have this up on GitHub. I'll have my GitHub account on here so you can watch it, or just email me when you're interested. And then the long-term goals of this. So what I want to do, and this is kind of my sales pitch, and I'm trying to find people that are interested to help me with some of this because I'm not going to have enough time to do it myself. The whole goal of what I really want to do is have some memory and execution tracing so that I can execute stuff, and for every instruction executed, and you can have hooks in Unicorn where you'll say, okay, before the memory is touched, I want to have a callback, and I can kind of watch for stuff. That's how I implemented breakpoints and single stepping. I want to watch that and also note when stuff is self-modifying code. I want to be able to save that and view it, and I want to render that in maybe the browser. I'm not a web programming guy, so this is where I really need some help. So if I save all those things off in JSON, can I use React or something to give me a really nice interactive post-mortem thing that I can run? Does anyone use Coverity by any chance? It's a static analysis tool, and they have a really nice thing where when it finds a potential path to a bug, you can go step by step clicking through it and the state of things. So what I want is to be able to have a browser-based thing that I can click through and see the state of things, memory and registers and things like that, so I don't have to run it through this again. It's just one page that I can kind of, there's JavaScript running it all. So anyone interested in that, or I know someone this guy over here, so yeah, if start kind of prototyping that at some point, and when you have something working, shoot me a ping, and I'd love to chat. And the other thing is, going back to where this came from, I had some microcontrollers or microprocessors that I didn't know where peripherals were in memory, and we had to do some crazy stuff to exfiltrate data out of them. So I'd like to be able to kind of emulate some peripherals and try to get a sense of, okay, this thing, I'm pretty sure this is a standard serial port core. So I'm going to emulate that and know that they're writing bytes out of UART. And some more tracing and doing things okay, I keep coming along this code path, and I know that there's instructions testing a bit. So I know they're pulling a flag, and I would kind of like to be able to start doing to the point where I can kind of infer what's going on at a more semantic level. That sounds crazy, so I mean that probably is a lot for a summer thing, but that's kind of what I'm doing. So if anyone's interested, I would love to talk more and get some advice. So this is a lot to throw at people. I mean, when I was working on this, I was thinking, man, computer architecture was an entire class I took, and then assembly was an entire class I took, and then even after that, tons of time just to really actually do anything, and I'm still learning. So for me, what I would say is, read the instruction set documents. If you Google this stuff, you're going to find tons of lecture notes, and then ARM exploitation materials. And as I kind of mentioned earlier, if you just only go for ARM exploitation, you're kind of missing some of the big picture. So kind of do a little bit of all of it. The instruction set's boring, but try to go back and forth a little bit. And then write code, test it and debug it. Now make it position independent like I was doing. Try to do that, take baby steps. And then one thing I wanted to have, and I was going to actually try to get done for the CTF, but time, was go implement an XOR shift 32 PRNG. and then XOR your code, and then write an unpacker that's going to unpack that code. So if you were to, try to throw a payload at something, you can make it different every time. So an IDS or something isn't going to latch on to some like common values in it, something like that. Make projects, and then go write some code, take some open source code, or in C or something, and then compile it with O0, O2, O3, and go disassemble it, look at it. How would you write it? How does it do it? Understand that. And then what does GCC do? What does Microsoft Visual C do? So, those two in particular, they have different calling conventions, so understanding how that stuff works. And this is kind of my approach. I mean, I haven't mastered this yet myself either, but that's kind of what I'm trying to do to get a better sense of things and develop more of a mastery of this stuff. So I'm always open to advice, and if people have questions, you can throw out some advice. And before I kind of finish up, I just want to give a big thank you to the BSides Rochester team. You guys have, some of you do, but the work put into this is huge. I helped out last year, and I could not believe how much effort and time is spent by these guys and gals. To the sponsors, of course, without them, we wouldn't have a lot of the cool stuff we do. To Frank and Sean for putting up with me and trying to finish these slides instead of playing card games and being generally annoying. And to my wife for putting up with me for working on slides on a nice Saturday afternoons where we should have been outside. And then most importantly, to all of you, it's awesome doing this. You make this super fun. I love meeting people. I like talking to people. So please come bug me or ask me questions or come tell me about projects you're working on. That's what I love. That's what I love about conferences. So. And with that, that ends my talk. This is just a cool picture I found. I'll put something on there. It's an ARM chip, and then a die shot, and then up here in the top left, it's kind of like where all the lines and stuff. I thought that was a really cool picture. So if you go find that on Wikipedia, but I can't pronounce the gentleman's name, so I don't want to butcher it. It's a Creative Commons licensed image. Go check that out, and it's huge. You can zoom in. It's awesome. So that's it. Anyone have any questions? Alex.
So what would you want to see in that prototype again that you're talking about for emulary? How do you say it?
Oh yeah, emulary. So yeah, the name actually. I was trying to find a cool name, right? Like there's a Dilbert comic that's like, they're sitting in a meeting room and the guy's like, so we need a name for the project. And they're like, that's the least important thing. And the guy's like, well, if we don't know what the name is, how are we going to know what it does? So I tried to find a cool name for it, right? I couldn't find anything. So it's Latin, and it's a conjugation of to emulate, but I don't know if I'm pronouncing it correctly, and I don't know Latin, so I'm going to just call it emulare, and so be it. In terms of what I want to see, so basically, you kind of saw how in my little GUI there. Let me actually, let's see if I can do this. Yeah, never start pulling up windows during your talk. That's tab. Alright, so now we have a mouse somewhere, I don't know. Anyway. So I have this view, right? And I don't have it on the right screen. So we have that view. Oh, I have my notes there. So imagine as I'm stepping through each of these instructions, essentially I want the information that's in each of the registers and all the memory regions I've mapped in. And now that can be kind of wasteful, so I'm trying to decide, does it make more sense to just have the deltas? So in that case, the implementation would have to kind of keep state, and I don't know if that makes sense in like a JavaScript application. Is that going to just blow up and be huge? Does that make sense? So those are the things. So essentially, I'm going to try to export either the deltas or everything all the time, or something like that, and I want you to parse that, and then kind of give like, let me open up IDA. Where am I? This is a terrible example. Let me switch that back over really quick, if I can find the mouse. So let's open yeah, that's fine. Let's find a function. Yeah. Okay, so I want something like this, where like, in addition to this assembly, I could, maybe not necessarily, the nice basic block view, but I'd like to be able to kind of go and like step through it as if I'm debugging it, kind of post-mortem, and then be able to say like, okay, it goes over here, and then I can kind of highlight over it, and then it would show me the state of registers or something like that. So that kind of, is that kind of picture making sense? And that'd be super cool because then I could get this execution trace and I don't have to like keep going in there and fiddling with it. I could just have one like kind of report document that I keep going back to all implemented in JavaScript. So I mean, I can write UIs, but like honestly, everyone that does the web stuff is so much better than I am. So, long-winded answer, I hope, and hopefully I just made a nice requirements document on your notepad there. So, thank you. Anybody else?
Sort of two questions. I was wondering about that, I guess, PC plus 2 instructions issue that you mentioned before. I guess one, I'm wondering if you would consider that sort of a bug in the way that Capstone actually disassembles the code, if it should point, just because IDA and Hopper do as well. And I guess two, I was wondering if you encountered any other sort of ARM peculiarities just along the way that are sort of in that line.
In terms of whether I consider that a bug, I'm going to say that I don't consider myself enough of an expert to make such a claim. Like maybe the developers do, I'm not sure. And then also like even if I thought I had the authority to say that, I'm not really sure that it's wrong. Like they're showing what it is, right? So like it's a matter of perspective, is what I guess is my answer. And I'm happy that they did it because I can look at like I showed you, I'm always looking at multiple tools. I don't just look at Binwalk or Binary Ninja or Hopper. I have all of them. All right, I'm going to be buying all of them when I have. Like I still got to get Binary Ninja, but between Hopper and IDA is usually what I'm going between. So yeah, I always have them both. And what's the second question?
Just if there are any other sort of ARM peculiarities that you.
There are, but on the spot, I'm still learning more all the time. But yeah, there's tons. I think how much time do I have left?
You have 15 minutes left.
Oh, really? Wow, that's super early. Some interesting things, like I just throw out some kind of neat things. So the first, if you dump something off a microcontroller, this isn't answering a question, it's just a random aside because I think. So the first region of code is usually going to be what's called like interrupt vector table. And this is basically where exceptions go to. If like different types of exceptions or interrupts occur, it's going to go here and then figure out where to jump to next. And a cool way that it's taught me to detect like, oh, okay, this is an ARM binary, if I don't even know the architecture, was that you're going to see words that are like something, 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 EA, and it's going to be a bunch of them. For if you look up the ARM IVT to see what position each of them mean and what they're used for. But that EA every few bytes is a quick, easy way to say, yeah, I'm looking at ARM. So that's kind of cool. So not like a weird quirk, but like an interesting observation. Other weird quirks that have got me. Well, like the first time you look at the store and load memory with full descending versus empty ascending, that's a little. It's all interesting. Yeah, I don't have any. I'm still diving into. I only have mastery of like a subset of it, and there's you've seen how big the reference menus are. So, I think if you're doing like a buffer overflow exploit, and someone might need to correct me on this. I feel like I read an article where you had to make sure you flushed a cache before, if you were writing into data memory, before you actually tried to execute it or something. You're not, that's true?
Yeah, on I think not just ARM, but I think MIPS as well.
MIPS as well. So that's kind of weird, and that caught me off guard because I was on a microcontroller, and it was kind of like I'm on a micro. I wasn't really thinking about cache, admittedly. What else is weird stuff? I don't think I have any other words. Let's chat later. Maybe I'll come up with another one for you. Any other questions, observations, praise? Yeah, I'll actually hang around here and have the tool up and play around with it if anyone wants to come check it out and chat more. So thank you very much for your time. I appreciate it.